In this video, I want to give a simple example of using parametric bootstrapping. But before I do, let's quickly review the concepts behind parametric bootstrapping. As we always do, we select a sample at random from our population, and then we make estimates, that is, we calculate statistics to estimate the parameters of that population. Unlike our parametric methods, in which what we do is look at a sampling distribution that is mathematically derived, we take an estimated population based upon our statistics, and using those statistics for our population parameters, we empirically draw many samples from that estimated population. We calculate the estimates of those and then look at the sampling distribution that's been empirically derived. So let's go ahead now and call up an R notebook and take a look at the parametric bootstrapping example. I'm going to start this example by drawing a sample from a known population. We don't do that in the real world of research. If the population is known, we're not going to research it. We're conducting this study because we want to know about the population. So what I'm doing now is a very Monte Carlo type move. That is, I'm temporarily stating that I know the population right now, so I can see how my sample results worked in estimating this population. But normally when you do bootstrapping, whether parametric or non-parametric, you don't know the population. So we're knowing it here just to get a sense of how this method works. Not just how to do it, but how well did it perform. So let's select a sample from a normal population that has a mean of 60 and a standard deviation of 8. I'm going to randomly select 50 units. I've done that. And I now have my sample. I can see it over here in my environment pane. Now we're going to erase our memories and forget about the population, at least until the very end. That is, we're going to act like this is real research. We don't know the population parameters, and we're going to use our sample to make the best guess that we can about the population. I'm going to build a bootstrap sampling distribution for the mean. Bootstrapping means that I'm going to generate many samples, just as we always do in any Monte Carlo method. I have reason to believe, perhaps based on the nature of the measure that I'm using, that the population underlying my observations is a normal distribution. So I'm making a guess of the mathematical form of the population distribution. Remember, I don't know that form. We've erased our memories. If I had reason to believe it was a uniform distribution, I would use that. If I had reason to believe that, say, the tails of the distribution are a bit heavier than normal, then I might go ahead and use a logistic distribution to be my underlying population distribution. But for our example, let's say we believe the population distribution is a normal distribution. What are the parameters of a normal distribution? It's the mean and standard deviation, mu and sigma. I don't know those. Okay? Again, remember, we've wiped our memories. What I can look at, however, are the statistics obtained from my observations. That is, I can calculate the sample mean and standard deviation. So I'm going to do that right now. And I see here I have a sample mean of 60.46. I have a sample standard deviation of 7.65. These are my maximum likelihood estimates for the mean and standard deviation of the population. Not only are they the statistics showing me what I obtained in my sample, but it is my single best guess of the mean and my single best guess of the standard deviation based upon the observations that I made. These are maximum likelihood estimates. Now I can start the bootstrap process. I'm going to draw 10,000 samples from a normal distribution, and I'm going to use these parameters. I'm going to use the same sample size as my actual sample. Remember, that was 50. And every time I draw a sample, I'm going to calculate the sample mean and I'm going to save it. So here's the number of samples, 10,000. My sample size is 50. And I am going to calculate 10,000 means. So right now I have as a placeholder 1 to 10,000. So here I've created a little for loop. I'm going to draw from a normal distribution a random sample of size 50, n. I'm going to use as the parameter of this distribution, this is the different part from what you've done in the past, I'm going to use as my parameter my sample mean as my best guess of the parameter. It's not the parameter, unless we were really, really lucky, but it's my best guess of the parameter. And also the second parameter, the standard deviation, I'm going to use my sample standard deviation as the best guess. I'm going to do this 10,000 times, each time drawing a new sample, and each time calculating the mean of that sample and storing all those means. Let's do it. All right, that didn't take long. Even though there were 10,000 times I drew a sample and calculated the mean. So I now have an empirical sampling distribution of means. Let's look at it. There it is. We should not be surprised that it looks normal. We don't even need to rely on the central limit theorem here. We were drawing from a normal distribution. Let's calculate our best point estimate of the population mean. Here it is, 60.45836. It's no surprise that we obtained this. We used our sample mean for our population mean. So with enough Bootstrap samples, the mean of the means should be quite close to our estimated population mean. Remember, our estimated population mean, I can still see it over here in my environment pane, is 60.4587, pretty close to 60.4584. Of interest here is the standard deviation of our means. That's going to be our Bootstrap estimate of the standard error. So our Bootstrap estimate of the standard error of the means is 1.08. Now we could use this value and the 97.5 percentile of the normal distribution, you know that to be 1.96, and we could create a confidence interval. Better yet, because we estimated the standard deviation, instead of using a known standard deviation, we might want to use a percentile of a t-distribution to create this interval. Remember, we estimated that standard deviation. But what's typically done is neither of these. Instead, we take this sampling distribution of the means and we cut off the tails of that distribution. So to do that, the first thing I need to do is sort my means. I'm going to sort them. Now for a 95% interval, how much do I need to cut off? So what I want to take is the middle 95%. So I'm going to cut off 2.5 off each end. I have 10,000 samples, so that's 250 off of each end. So I want to keep, for my confidence interval, from the 251st value, remember the means have been sorted in ascending order, I want to retain the 251st value as the lower bound of my confidence interval, all the way up to the 9,750th value as the upper bound of the interval. So that's what I'm doing right here. So here is my interval. So I'm 95% confident that the population mean is between 58.34 and 62.61. All right, let's leave the world of research. Let's travel back into make-believe one more time, and we're going to get our memories back. The original population I started with, the one we are not usually going to have access to, but this time we did just to see how well this worked. That had a mean of 60. So indeed, I've captured the mean here. The mean is within 58.3 and 62.6. Our mean is 60. I'm 95% confident the mean is somewhere in there, and all I'm saying here is indeed it was. This leads me to want to do a little Monte Carlo study. So even though bootstrapping is itself a specialized Monte Carlo, I want to do another kind of Monte Carlo study, the regular kind I'm used to, and see how many times I capture the mean if I use this parametric bootstrap 1,000 times. So I'm going to do everything that we did above. That's everything down here with the bootstrap sample, doing it over and over again 10,000 times. I'm going to do everything that I did above, but this time I'm going to start with new sample parameters. So I'm going to take, that sounds funny, sample parameters, but that's what we're doing. We're taking the sample estimates to use them as our parameters for our best guess for the population. So I'm going to take my sample, and every time I'm going to take a new sample, all 1,000 times, this can get confusing because we're doing 10,000 bootstraps, but the bootstrap is based on the same sample. I want to repeat that with different samples 1,000 times. So I'm going to have a mean of 60, standard deviation of 8. Again, remember, I'm in the world of make-believe here. I'm saying, imagine I know my population. I'm going to take a sample mean, I'm going to take a sample standard deviation, and I'm going to use those in my 10,000 bootstraps that I do. Each time I'm going to sort my means, look at the lower and upper bound, and I'm going to see if my actual parameter of 60 is at least the lower bound and no more than the upper bound. It's somewhere in that interval. If it is, I'm going to say got it. And I'm going to take my got it statistic, my got it variable rather, that I set to 0 up here. I'm going to add 1. So let's see how many times we capture the actual mean. Now, this is one of those situations where I'll be saying goodbye to you for a little bit, but you won't know it because in just a second I'll be returning. But this is going to run for a while because remember, it's doing this 1,000 times where each time it takes 10,000 bootstrap samples. So there's a lot going on here. So I'll see you at the end of this. Okay, I'm back. While I was away, because it was actually I'm the one that was away. You're still here in this video, and no time at all hardly has passed for you. But several minutes went by for me in order to do this, and now it's the moment of truth. What percentage of the times did we capture the population mean? So I'm taking got it, dividing by 1,000, because I did 1,000 Monte Carlo simulations, timesing by 100 to get a percent. It is about 94%, not bad. We had a 95% confidence interval and we're off by 1 percentage point, not bad at all. Now, do we really need to put all this code in every time we want to do a parametric bootstrap in R? No, of course not. There are a number of packages to do bootstrapping. You should do some exploring. I'm going to go ahead and use the boot library. So I've already installed it on my system. If you want to follow along, you'll need to install it on yours unless you have it already. I'm going to load that boot library. Now the boot function that we're going to use is quite general. That's good news and bad news. It's good because with a general function, you can do pretty much anything. It's bad because there's a little bit of work to set it up because it's so general. Now you could always take this and store some specific version of it behind the scenes. In fact, you could even take the code that I have here and take it and copy it and store it as a function that you can use in the future. We have to specify how we're going to generate our data because remember, doing parametric bootstrapping doesn't mean that you're always going to use a normal distribution. Maybe you're going to use a uniform distribution. Maybe you're going to use a t-distribution, and a t-distribution only has one parameter, whereas the normal distribution has two and the uniform distribution has two. So we don't even know how many parameters we're going to have. So that's why we have to specify how we're going to generate the data. Now we drew from a normal distribution. Let's go ahead and get our original sample estimates again so that we're using the same sample we did when we started this all. I'm going to write a small function to generate the data, and here it is. So what's happening in this function is that I'm going to hand it a sample. I'm going to get estimates from that sample, and then those estimates are going to be used. In this case, there are two of them, mean and standard deviation. Those estimates are going to be used along with the sample size, that's the length of my sample, in order to generate a new sample from a normal distribution. That's the basic function that's going to get called. And remember, it's going to get called many times, depending upon how many times I want it to be called, as I'll show you here in a moment. We also could be doing this bootstrap for any statistic. It doesn't have to be the mean. So we have to write a second function. The first one is to tell, here's how you're generating the data, and here's what distribution I'm going to use. The second one is, here's the statistic that I'm studying. So here I wrote a very simple little function that basically, when we hand it a sample, we're going to calculate the mean of the sample, but furthermore, remember, we're going to be calculating many means, and they're going to be stored in a vector just like when we did it before. So we have to take the sample and indicate a variable here with the number of the sample. So those two things need to be passed to the function, and that will happen automatically once we specify the parameters of our function, which is called boot. So here it is. So what I'm starting with is my data. Remember, I'll only have one sample. Earlier in this notebook, I created many samples because I was doing my own bootstrap function. But now we're going to use a built-in function, so we're just going to give it one sample. So here is the sample up here. Remember, I called it my sample. There it is. That's the one sample that I have. I'm going to feed it that one sample. I'm going to tell it I want a parametric bootstrap, because remember, there are also non-parametric bootstrap methods. I'm going to tell it that I want to generate the data using my getData function up here. So this is wanting you to give it a function, which I've done. And then I'm going to give it my maximum likelihood estimates, and there are two of them here. They are for my sample mean and my sample standard deviation. And then I'm going to tell it what function is going to calculate my statistic. And I called that one my stat. So I'm not only passing a function for the normal distribution generation, I'm also passing a function that will calculate the mean. And then I finally get to the point where I tell it how many times I want to do a bootstrap, and I've told it 10,000. I'm going to run this, and it didn't run because I did not load my other stuff. Let me try that again. I did not load the function. There it is. There it is. Now we should be good to go, and we are. And here it is. Now I don't have a confidence interval yet. It tells me that my original mean was 60.458. It tells me how far off I was with my mean of my means. That's our bias. And it tells me my standard error. Those numbers should look pretty familiar to you from when we did the bootstrap by hand. To get the confidence interval, notice I stored the results from boot in boot results. There's a number of things that we can get. We can look at the sampling distribution. I'm just going to go ahead and get the confidence interval. And there are multiple types of ways that it will generate those. I'm going to use the basic way, which is the way where you cut off the 2.5%. And by the way, 95% is the default for the confidence interval. So therefore, I've not put in the confidence level. But if you look at the help for boot.ci, you can see how to change that. I'm going to get a basic confidence interval. And here it is, from 58.30 to 62.58. So keep in mind, this is based on building an empirical sampling distribution and trusting that you've selected the right distribution. We probably will not know what the right distribution is. So even though we are doing bootstrapping which is a Monte Carlo method. We're utilizing some parametrics here, and this is a course on non-parametric statistics. So if we're not certain about what is the right distribution, and I suspect most of the time if you're using bootstrapping, you're not certain, we should move on to non-parametric bootstrapping, which I will do in the next video.